Hello, everybody. My name is Masood Olia, and I'm a faculty in the School of Engineering at Wentworth University, and I'm here with another video, this time related to the topic of mechanics of materials, and in particular related to drawing a shear bending moment diagram for a beam, which is made of wood, and trying to figure out the dimension of this beam, like the width and the depth of this beam, the width. So it says this beam is made of Douglas fir, having an allowable shear stress of 1400 psi. So we don't want the bending stress, normal stress in this beam to be larger than 1400 psi, and an allowable shear stress. This is based on the strength of this wood, right, to be more than 700 psi. So this would be the transverse shear stress due to the shear load. So based on that, determine the width of B such that the height would be 2B. So whatever the width is, if it's 3 inches, we calculate it to be 3 inches, then the height would be 6 inches. And in the process, obviously, we have to draw the shear bending moment diagram for this beam because obviously we need the values of the shear load, maximum shear load, right, and maximum bending moment. So let me go ahead, guys, and stop my camera if I could. All right, so that way you don't get distracted, so I can flatten my iPad as well. All right, sorry for the noise that I'm generating for doing that. All right, guys, so let's go and solve this problem. So clearly we have to draw the shear bending moment diagram, which means we need to figure out the reactions here. So I'm going to call this point A. So we have obviously a vertical reaction just in the y direction. I'm going to call this point B. So we have by here. All right. So now let's go ahead and let me make this a little bit thinner. All right. So you guys know that what we have to do is to start by figuring out these reactions. So I'm going to go ahead and take moment about A, say it equal to 0, say counterclockwise positive. So we have by times 6, right? And then we have this 900, which is on the other side. So that's actually going positive. And then you know that this distributed load can be changed to a concentrated load, which is the area 100 pound-foot times 9, right in the middle. So that makes it 4.5 feet from here, right? And that's going negative. So 900 times 4.5. All right. So let's go ahead and solve by. By should be 225 pounds. So I'll put it right here for you. And just balance forces in the y direction and get your AY. So AY plus BY minus this 900 minus this 900 equals 0. Go ahead, put the value of BY here, and you get an AY of 1,575 pounds. Okay? So clearly that's the first thing we have to do. Let me go ahead and get rid of some of these things that we don't need now. Obviously, you cannot use the concentrated load here. It has to be back to distributed load in order to draw the shear bending moment diagram. So let's go ahead and now draw the shear bending moment diagram. So let's go ahead and remove this a little bit now. So you know how to draw a shear bending moment diagram. You can watch some of my videos. Just do a search, shear bending moment diagrams. So I'm going to draw the shear. I do need the value of maximum shear load, absolute maximum shear load for this problem, right? So you know you have to go down. Let's use blue. Oop, that's very thick. Make it thin. All right, so let me just erase this blue. So yes, just use this. So 900, right? In fact, let me just go a little bit further because it looks like we do have. Okay, so let's call this minus 900. Shear remains constant, right? Then you go up 1575. that should put you at 675. Let's say that's 675. Of course, this is not to scale. Then you add negative of this area to it, which is 600. So 675 minus 600 will put you at 75, right? We know that's going to be linear, right? Whenever you have a uniform distributed load, your shear changing linearly. So 75, you add 225 to it, that should bring you to 300. So let me actually move this 75 over here if I could. So 75 plus 225, that's 300. And then 300, you add not this area, which is also 300 negative of the area. So that should bring you to 0 linearly. So that's your shear diagram. Let's go ahead and continue with the moment diagram. I'm going to plot the moment in pound-foot. Be careful with the units versus x in feet, right? So I'm going a little bit faster because I'm assuming that you know how to draw shear bending moment diagrams, right? So remember, area under the shear is the net moment, right? Net bending moment. So this area is minus 2,700, right? That area, let's see what that area is. I have to use my calculator. I have it somewhere here. So area of that trapezoid can be determined. If you don't know the formula for a trapezoid, just go ahead and break it into rectangle and triangle. This area becomes 2,250, and this area with triangle is 450. Okay, so how does our shear moment diagram going to look like? So starting at 0, we add negative 2,700. That should put us at negative 2,700 linearly. Then we add 2,250. That should bring us exactly at minus 450. Again, this is not to scale, but this is going to be parabolically and a concave down. And then minus 450 plus this 450 should put us at 0 again parabolically. All right? So what do we need from these two diagrams? What are the important numbers? We say, okay, the maximum absolute shear load. Sign is not important, guys. All right? So it's a 900 pound. And this is a symmetric cross-section. So what's important to us, again, is the absolute maximum moment, which is 2,700 pound foot. One thing you want to do right away is to change this 2,700 pound foot to pound inch. So if you do that, you get 32,400 pound inch. That's very important, guys. Otherwise, you mess up the units. Let's go back up, guys. What are our constraints here? We have two constraints. The allowable normal stress is 1,400, right? So that's the maximum 1,400 psi. This is based on the strength of this material, Douglas fir, good, pine, right? And tau allowable is what? 700 psi. So for this, we use the maximum moment, right? So for example, just before I move down, what's the area? We need the area of this. B times 2B. So the area is 2B squared. And what's the moment of inertia with respect to the centroidal axis? 112 B 2B cube. I'm sorry. B times H cube, right? But H is 2B. So that's 8 over 12, which is like 2/3 B to the power 4, right? So hold on to those. Let's come down. So first, I'm going to work on the sigma. Sigma max, is MC over I, Fletcher formula, right? Maximum stress. So what is the maximum stress for us? It's 1,400 psi. So let's go ahead and plug in. Maximum moment. Remember, unit was important, 32,400 pound inch. C is what? C, remember, guys, it's half of the depth. So C actually becomes half of 2B. So that's B. And what is I? I determined I for you here. 2/3 of B to the power 4. Go ahead, solve for B here. And B happens to be 3.26 inches. But we haven't calculated our dimensions based on the transverse shear load, which has a limit of 700 psi. So what I'm going to do, I'm going to say, okay, tau max is what? You guys know the formula is VQ over IT. But fortunately, for a solid rectangle subjected to a transverse shear, we know that the maximum shear load can be calculated easier. And that happens obviously right on the centroidal axis. I was going to write tau max actually here, right? Because tau is 0 here, due to that, 0 here. You can watch some of my videos on that if you want. But it could be shown that that is actually 3/2 V over A. So let's go ahead and put our constraints of 700 psi here. We don't have to really do anything. The maximum shear load that we got here was 900, right? Divided by what? Area. I said area is what? B times 2B. I had it here for you, 2B squared. Go ahead, solve for B again. And this time you get B equal what? Much smaller. So now you have two choices, either this one or this one. Obviously, when it comes to dimension, you have to go with the larger dimension. So this beam should be at least 3.26 by inches by what? By twice that, 6.52 inches. So you see what really controlled the design, guys, here, what really controlled the design, it was not the shear stress, because shear stress in design is very, its effect is minimal. It's usually the bending stress. So you see our calculation of the dimensions, the limitation was based on that normal stress. Let me put my video back, guys, so I can say goodbye to you. Here we go. I could look at the camera correctly. So as always, guys, I really appreciate if you like the video and subscribe to my channel. I always making new videos whenever I have time. This is a busy time of the season, getting ready for the final exams and so on. But the topics that I pick is dynamics, vibrations, mechanics of materials, statics, and so on. All right, guys, take care, and I will see you soon.